Okay, chapter 17, day 3. In class we did a dice rolling activity in which we let 1 through 5 be success and 6 through 20 be failure. If you remember, we rolled the dice and we rolled it a certain number of times and we counted the number of successes. And the reason why we're doing this is we're looking at how does the graph behave of the expected number of successes that we should be getting when we make a certain number of rolls. The whole goal in mind being at some point in time the trials are going to get large enough that we don't want to use binomial PDF and we want to maybe start using the normal model if we can. So this activity was designed to show how many rolls it might take before things start looking more normal. So we had 1 through 5 be success, 6 through 20 failure. You all have this graph on your paper already drawn. You don't have to redraw it again. But for 5 rolls, all classes took on a shape similar to this. This might not be exactly your data, but it was very similar. The average was somewhere around 1 or 2. That was the green arrow that you guys told me where to put. And we noticed that it was skewed right. We did not get a tail out the back because you can't get negative successes. So 5 rolls, fairly skewed, very small standard deviation. And then we rolled 20 rolls. And after 20 rolls, started to get not quite as skewed, but still skewed. We still really don't have a tail going this way, again, because we can't really get into the negative successes like you can get all the way out to 13 here. The average is somewhere around 5 is what we found it to be when we balanced out our graph, and still slightly skewed to the right. So then we bumped it up to 40 rolls for this scenario. And at 40 rolls, we noticed, and your graph was similar to this, it might not have been identical, but it started to look more symmetric and started almost to be normal looking. And you could tell it starts to get more of a tail here to the left. There's room for a tail. We could have gone 6, 5, 4, 3, 2 all the way down to 1 if we wanted to. And so when the average gets out far enough away from 0, it gives us room enough to have a tail. When the average was expected to be about 1 to 2, no room for a tail. When the average was expected to be around 5, a little bit of room for a tail. When the average gets to be around 10, that's when we start to have enough room for a tail on the back side. Okay? And we have enough room for a tail on the front side. Starts to get more symmetric, starts to get more normal. And the sample size was 40. Now again, that's kind of on the edge of, do I really want to look at the probability that I get at least 23 successes? Well, then I got to do binomial PDF for 24, 23, 24, 25, all the way up to 40. That's a lot. Or 0 through 22 and take away from 1. That's a lot. This is where we start to get on the edge of maybe there's a better way. And the better way is the fact that we're starting to get this normal looking. All right? So we wrote the next part in our notes. We all wrote the fact that we can have a normal approximation. And all classes got this down in your notes. You don't have to rewrite it. The normal approximation for the number of successes that we would expect in this binomial model is given by the formula n times p. And we came up with that in class. We said, 5 trials, probability was 0.25. We should have about 1.25. And if we look back, sure enough, somewhere around 1.25. N times p, 20 rolls, 0.25 should be about 5. We were pretty close. 40 rolls should be about 10. Most classes were right on. And we also noticed, though, that the deviation got larger and larger and larger as n got bigger. Well, we have a formula, and not all classes got to this, but this is okay. This is where you want to write down if you don't have this. The standard deviation is a formula, the square root of n times p times 1 minus p. So if n is, let's say, 40, and p is 0.25, n minus p would just be 0.75. The square root of that would be the expected standard deviation for the number of successes. Okay, but here's the thing, and we talked about this before. This is not good for 5 rolls. It's not good for 20 rolls. It's only good in certain situations. So for the first time, we're going to talk about the conditions that we need to meet to use the formula. And so from here on out, we might have to check to make sure we can use the formulas. Otherwise, we're not allowed to use them. They're the conditions that we need to meet. So let's take a look at the conditions. So the conditions to use the normal approximation. All right, we have conditions that we have to meet. And right now we have 2 conditions. One, the 10% condition. All right, the population that we're pulling from must be greater than 10 times the sample size. This will give us independence in the problem. Or each trial must be independent. When we're shooting the eraser, each trial is independent, we meet this condition. Otherwise, what we're pulling from has to be big enough to meet the condition. I will explain what I mean by that tomorrow in class. Okay? So for right now, let's just get that down and I'll explain it more. It's easier for me to explain it in person. The other condition that we have is what we call a success-failure condition. And the success-failure condition purely is the fact that the expected number of successes and or failures must be greater than or equal to 10. And that goes with our pictures that we just did. If you look back at our picture, the expected number of successes, or I could have said 1 through 5 is failure, 6 through 20 is success. I don't care which way you slice it. All right? The expected number needs to be up around, not 5, but up around 10, so it allows us to have a tail in the other direction. When this expected number gets to be around 10, then we can start using a normal curve approximation. So what do? We take a look. Does n times p, is that greater than or equal to 10? Is n times 1 minus p greater than or equal to 10? If those things are met, we've met the condition. And once we've met those conditions, we say that it is okay to use the normal model. If we meet all of those conditions, we state that it's okay to use the normal model. We tell what model we're using, and we've told why it's okay to do it. So let's take a look at a problem from the archery girl again. Okay? An archer, shooting a bow and arrow, that is a 70% shooter takes 300 shots. What's the probability that she makes at least 240 of them? So again, I could do binomial PDF, 240, 241, 242, all the way up to 300. It would take me a long time and I could get the right answer. Or I say to myself, wow, that's a pretty big sample size. Who wants to do all that work? Let's see if we can use the normal approximation instead. So let's check our conditions. 1, assume each shot is independent. Every time she shoots, it's independent. The previous shot does not affect the next shot. We're going to assume that to be true. 2, I'm going to check my n times p. So n is 300, p is 0.7. 300 times 0.7 is 210. Ooh, that's definitely greater than or equal to 10. Check mark there. N times 1 minus p. Got to see if that's bigger than 10. Because if your failures aren't bigger than 10, then you get no tail in the other direction. 300 times 0.3 is 90. Ooh, plenty bigger than 10. So it is definitely okay to use the normal approximation. You must make that statement to get full credit. So for example, if the conditions are worth a couple points, one of the points that you get credit for is stating what it is okay to do. If you leave that off, you don't get full credit. So let's lay out our formulas. The average number of successes that we would expect is 210. All right? So again, this is the average number of successes we would expect is 210. Standard deviation, we just fill in the formula. These formulas are given to you on your test. All right? On your final. I don't give them to you. You can purchase them again for points. So standard deviation, fill in the blanks. Standard deviation is 7.9. So what does that mean? On average, she's going to make 200 successes, 210 successes, with a deviation standard of 7.9. Let's go back a second. Average number of successes about 1.5. Standard deviation maybe a half or 1. Average number of successes around 5.5. Standard deviation of maybe 2-ish or so. Average number of successes 10. Standard deviation of who knows, 1 or 2, 2-ish. It's a measurement of spread, of variability. So if we go to the archer, average number of successes 210, standard deviation is 7.9. Now, we said it's okay to use the normal model. So what am I going to do? I'm going to draw a normal model. Average 210, and we said what's the chance that she makes at least 240? So 240's out here, at least we shade. Gotta go z-scores. 240 minus 210 divided by our standard deviation, 3.77. I already know right away more than 3 standard deviations is pretty rare. It's probably going to be pretty small. Okay? So the probability that z is bigger than this, we looked this up in the back of the book. And if I look up 3.77 in the back of the book, it tells me 0.9999. And that's this in the back of the book. 1 minus that is the upper part, which is 0.0001. All right? If you wanted to, you could have done normal CDF. Again, lower bound, z-scores 3.77, lower bound, upper bound positive 99, and you would get the same answer. Again, second VARs, normal CDF, lower bound, upper bound, you'd get 0.001. They might say 1e to the negative 4, which means back it up 4, 0.0001. Okay? So what does that tell us? There is a very small chance, this is our conclusion. We start writing conclusions now. Okay? Conclusion. There is a very small chance that she could make at least 240 bullseyes. All right? Pretty small chance. It's like 1 in 10,000. So this is the normal approximation to the binomial. That's what today's focus is. And it's all about taking a situation that is binomial, all right? Success or failure, probability of success, number of shots, how many do we want to make out of the total, and using the normal curve so that way we don't have to do 240, 241, 242, 243, all the way up to 300. We got to check conditions. If the conditions aren't met but they're close, maybe we'll make a disclaimer at the end and we'll talk about that in class. But check your conditions that you can use it. State if you can use it. Find your mean and standard deviations, just cranking out some formulas. Lay out your normal curve. Find a z-score, chapter 6. From the z-score, get a probability either from the back of your book or from normal CDF. I don't care which one you pick, but you're going to tell me what you're doing. And based on this result, we write a conclusion. And that's chapter 17, and that's it for the chapter.